this video tutorial, I'm going to show you how to solve 10 different types of milliequivalence calculations questions, and we are starting right now. Hello, this is Dr. Dankwa, and if this is your first time here and you like to learn pharmaceutical calculations tips, tricks, and strategies, then start by subscribing and clicking the bell so you don't miss anything. So the questions I'll be solving in this video tutorial come directly from the RxCalculations.com website. Now, if you want to take the quiz before going through the video tutorial, then head over to RxCalculations.com/quizzes. I'll put a link in the description, and once you're on the quizzes page, there are several quizzes, but what you want to do is click on the milliequivalence quizzes, click Start Quiz, and it's a timed quiz. You have 10 questions to be completed in 20 minutes. So let's get right to it. This question says, how many 750 milligram potassium chloride tablets should a patient take to obtain 30 milliequivalents potassium chloride? Molecular weight of potassium chloride is 74.55. You're supposed to round the answer to the nearest whole number. So let's start off by putting down the equation. So milliequivalence is equal to the weight in milligrams divided by molecular weight times the valence. So from the question, we've been given the amount of milliequivalents that the patient needs to take. So the strategy here will be to determine how many milligrams represents the 30 milliequivalents, and once we found that value, we will then divide that by the 750 milligrams which is present in each tablet. So in order to do that, we already know what the molecular weight is. It's 74.55. So our next task is to figure out what the valence of potassium chloride is. So potassium chloride, which is KCl, when you put that in an aqueous environment, it's going to dissociate into a potassium cation and a chloride anion. Now the valence is the absolute of either the charge of the cation or the charge of the anion. So in our example, in both cases, the valence of potassium chloride is 1. So what we can do next is we can substitute the values into the equation. We have 30 milliequivalents being equal to the weight in milligrams divided by molecular weight, which is 74.55. We can multiply that by the valence, which is 1, and we solve for milligrams. So that implies that your milligrams is going to be equal to 30 times 74.55 divided by 1. And that is going to be equal to 2236.5 milligrams. So we can now proceed to determine the number of tablets that the patient needs to take. So for number of tablets, what we want to do is to take the 2236.5 milligrams, and from the question, each tablet contains 750 milligrams of potassium chloride. So we can cancel out the milligrams, and we end up with 2.98, which is approximately 3 tablets. Let's take a look at this question, which says, calculate the amount of magnesium sulfate heptahydrate with molecular weight 247 in grams required to compound 200 capsules, each containing 10 milliequivalents magnesium sulfate. Round answer to the nearest whole number. Do not include units. So let's start off by analyzing the question and figuring out a path to the solution. From the question, we've been given the milliequivalents of magnesium sulfate in each capsule. We know the total number of capsules, and so we can find the total milliequivalents that is needed. So once we've determined that, we'll then plug it into our equation and then we'll solve for quantity in milligrams and then convert that to grams. So the first thing we want to do is put down the equation. Milliequivalents is equal to weight of substance in milligrams divided by the molecular weight times the valence. So we've been given the molecular weight to be 247. We go ahead and find the valence. So magnesium sulfate heptahydrate is actually going to be MgSO4, and then you have 7 molecules of water attached to the compound. So when you put the magnesium sulfate heptahydrate into an aqueous environment, the 7 molecules of water is just going to go into the water, and then the magnesium sulfate is going to dissociate into a magnesium cation and a sulfate anion. And so the valence of the compound will be the absolute on either the charge of the cation or the anion. And so the valence of the compound is going to be 2. The next thing that we need to do is determine the total milliequivalents that is provided by 200 capsules, each containing 10 milliequivalents magnesium sulfate. So we can say total milliequivalents is going to be given by 10 milliequivalents in each capsule, so per 1 capsule. And we have 200 capsules, so 200 capsules. The capsules cancel out, and your total milliequivalence is going to be 2,000. So we will have 2,000 equals quantity in milligrams divided by the molecular weight, which is 247, times the valence, which is 2. And now we can go ahead and solve for our unknown, which is the quantity in milligrams. So milligrams is going to be equal to 2,000 times 247 divided by 2. And that gives us 247,000. But the units are in milligrams, and the question is asking for quantity in grams. So we do a quick conversion where you have 1,000 milligrams being equal to 1 gram. So the milligrams cancel out, and you end up with 247 grams. Let's take a look at this question, which says, how many milligrams of KCl, molecular weight 74.55, is required to make 240 milliliters of a KCl solution containing 20 milliequivalents per teaspoonful? So in this question, we are required to find the number of milligrams. And so what we can do is to start off with the milliequivalence equation. And so the equation is milliequivalents is equal to the weight of substance in milligrams divided by the molecular weight times the valence. So we already know what the molecular weight is from the question. It is 74.55. And so what we need to do next is find what the valence of KCl is. And so KCl, which is potassium chloride, when you put that in an aqueous environment, it dissociates into a potassium cation and a chloride anion. And so the valence is going to be the absolute of either the charge on the cation or the charge on the anion. So in either case, the valence of the compound is 1. The next thing we need to do is determine the total milliequivalents present in the 240 milliliter KCl solution. And so the total milliequivalents would imply that we'll start off with a 20 milliequivalents per teaspoonful. We do a quick conversion. 1 teaspoon is equivalent to 5 milliliters. The volume that we are preparing is 240 milliliters. So the milliliters cancel out, the teaspoon cancels out, And then we can now determine what the total milliequivalence is. And so we'll end up having 960 milliequivalents. And so the next step will be to substitute all the values into the equation. We have 960 being equal to the weight of substance in milligrams divided by the molecular weight, 74.55, times the valence, which is 1. We can go ahead and solve for the quantity. So milligrams equals 960 times 74.55 divided by 1. And that's going to be equal to 71,568 milligrams. This question says how many milliequivalents of sodium are contained in a liter of normal saline. Round to the nearest hundred, do not include units. So from the question, we are looking for milliequivalents. And so we can start off with the equation. Milliequivalents is equal to the weight of substance in milligrams divided by the molecular weight times valence. So there are a number of things that are implied from the question. Normal saline actually is sodium chloride. And so the molecular weight of sodium chloride is 58.5. Then we also need the valence. And so when we take the sodium chloride, which is NaCl, and put that in an aqueous environment, you're going to end up with a sodium cation and a chloride anion. And so the valence is the absolute charge of either the charge on the cation or the charge on the anion. And so the valence is going to be equal to 1. Now the next term that we need is the quantity in milligrams, and so we pick that information from the word normal saline. And so normal saline implies 0.9% sodium chloride solution, which means that you have 0.9 grams of NaCl in 100 milliliter. But we have a 1 liter preparation, which actually is 1,000 milliliters. So we need to determine how many grams of sodium chloride will be in the 1 liter, which is the same as 1,000 milliliters. So we can solve for x. X is going to be equal to 0.9 grams times the 1,000 milliliters divided by 100 milliliters. The milliliters cancel out, and you end up with 9 grams. But you need a quantity in milligrams, and so you need to do a quick conversion. So 1 gram is 1,000 milligrams. The grams cancel out, and you end up with 9,000 milligrams. So now we can put all of the information into the equation, and that would imply that you have milliequivalents being equal to 9,000 divided by 58.5 times 1. And that is going to be equal to 153.85. So this question says how many milliliters of a 10% magnesium chloride solution contains 30 milliequivalents of magnesium ion. Molecular weight of magnesium chloride is 95.21. Round answer to the nearest tenth. Do not include units. So here, the goal is to find the volume of a 10% magnesium chloride solution which contains 30 milliequivalents of magnesium ion. So what we want to do is start off with the equation, which says milliequivalents is equal to the weight of substance in milligrams divided by the molecular weight times the valence. So for us to ultimately find the volume of the 10% magnesium chloride solution, the first thing we will do is to find the quantity in milligrams. So we already know the molecular weight of magnesium chloride, which is given as 95.21. The next thing we need to find is the valence. So magnesium chloride is MgCl2, And when you put this in an aqueous environment, it's going to dissociate into a magnesium cation and 2 chloride anions. So the valence of the compound is going to be either the absolute of the charge on the cation or the absolute of the charge on the anion. So if we use the cation, which is the magnesium cation, then the absolute of positive 2 is going to be 2, and so the valence is 2. So we know the molecular weight and we have the valence, and so we can substitute all these values into the equation. And so we'll end up having 30 milliequivalent being equal to the quantity in milligrams divided by the 95.21, which is the molecular weight, times 2, which is the valence. So we can go ahead and solve for the quantity in milligrams, and so we have milligrams going to be equal to 30 times 95.21 divided by 2, and that's going to be equal to 1428.15 milligrams. But because we have the percentage strength of the magnesium chloride solution as 10%, which actually means 10 grams of magnesium chloride in every 100 milliliters, we want to convert this milligram quantity to grams. And so we do a quick conversion where 1,000 milligrams is equivalent to 1 gram. So we cancel out the milligrams and we end up with 1.43 grams. So now we know the quantity in grams, but ultimately we need the volume in milliliters. And so we're going to make use of the percentage concentration, which is the 10%, and that implies that you have 10 grams of magnesium chloride in every 100 milliliters. And what we have is we have 1.43 grams, and so we need to figure out how many milliliters that actually represents. So we can go ahead and solve for X, and X equals 1.43 grams times 100 milliliters divided by 10 grams. And so the grams cancel out, and that gives us 14.3 milliliters. So this question says, how many milliequivalents of chloride is provided by an intravenous TPN solution containing 40 milliequivalents of sodium chloride and 25 milliequivalents of potassium chloride? Round to the nearest whole number. Do not include units. So what is happening here is we want to find the milliequivalents of chloride, but we have two sources of the chloride, which would be the sodium chloride and potassium chloride. And so what we want to do actually is to start off with the equation for milliequivalents. And the version of the equation we want to use is milliequivalents is equal to millimole times the valence. So let's start off by taking a look at how many milliequivalents of chloride is provided by the sodium chloride. So now when you take the sodium chloride, you have NaCl. That breaks down in an aqueous environment to a sodium cation and a chloride anion. But notice that from the stoichiometry, you have 1 mole of sodium chloride giving you 1 mole of a sodium cation and 1 mole of a chloride anion. And the reason that is significant is it means that if you know the millimoles of sodium chloride, you basically have the same millimoles of sodium cation and the same millimoles of a chloride anion. And so for the first example, we can go ahead and find the millimoles provided by the sodium chloride. So we will have 40 milliequivalent is equal to millimole times the valence of sodium chloride. Now the valence of sodium chloride is actually 1, so your millimole is equal to 40 divided by 1, which is 40. So now this implies that you actually have 40 millimoles of sodium chloride. So now when we looked at how the sodium chloride breaks down into a sodium cation and a chloride anion in an aqueous environment, we noticed that 1 mole of sodium chloride gives you 1 mole of a chloride ion. And so since we have 40 millimoles of sodium chloride, it implies we have 40 millimoles of the chloride anion. And so the milliequivalents we get for the chloride from sodium chloride will be 40 times the valence of the chloride ion, which is 1, and we end up with basically 40 as well. So 40 milliequivalents of chloride. Now we can do a similar thing for the potassium chloride. So KCl breaks down in an aqueous environment to a potassium cation and a chloride anion. So notice that 1 mole of potassium chloride gives you 1 mole of potassium cation and 1 mole of the chloride anion. So we can go ahead and determine the millimoles of the potassium chloride, and that will be given by MEQ over valence. And the milliequivalence of the potassium chloride is given as 25. The valence of the chloride anion is 1, which gives you 25 millimole. So we have 25 millimoles of potassium chloride, but also implies that we have 25 millimoles of the chloride ion, which we're getting from the potassium chloride salt. So we can go ahead and find the milliequivalence of the chloride, which is going to be 25 times the valence of the chloride ion, which is also 1. So we end up with 25 milliequivalents. So the total milliequivalents for the chloride ion will be equal to the 40 milliequivalents from the sodium chloride plus the 25 milliequivalents, and that will be equal to 65 milliequivalents. Let's take a look at this question, which says a physician orders potassium chloride 12 milliequivalents in normal saline 100 milliliter. Calculate the amount of potassium chloride to be added to the normal saline bag if the pharmacy stocks 4 milliequivalents per milliliter KCl. Round to the nearest whole number. Do not include units. So in this question, the expectation is to calculate the volume of potassium chloride that you need to put into the 100 milliliter bag to give you 12 milliequivalents. So in this question, we do not need the equation. Rather, what we want to do is make use of the concentration that has been given to us. And so we will start off with the 4 milliequivalents in 1 milliliter, and we set up a proportion to determine how many milliliters will be required to give us the 12 milliequivalents. And so we go ahead and solve for x, which is our unknown. So x equals 12 milliequivalent times 1 milliliter divided by 4 milliequivalents. The milliequivalents cancel out, and so the answer is 3 milliliters. This question says, calculate the amount of calcium chloride dihydrate, molecular weight 147 in grams, needed to make a 250 milliliter solution with a final concentration of 2 milliequivalents per milliliter. Round answer to the nearest 100. Do not include units. So we could start off by putting down the equation. Milliequivalents is equal to weight of substance in milligrams divided by the molecular weight times valence. And so the strategy will be to first determine, using the equation, the amount of the calcium chloride in milligrams, and then subsequently doing a conversion step to convert the milligrams to grams. So we've been given the molecular weight of calcium chloride dihydrate as 147. The next thing we need to do is determine the valence of the calcium chloride dihydrate. So calcium chloride dihydrate is given as CaCl2.2H2O. When you put this in an aqueous environment, it's going to break down to a calcium cation and 2 chloride anion. So the 2 molecules of water attached to the calcium chloride goes into the water, and so it doesn't really contribute to the ions that are present when the calcium chloride dihydrate is dissolved in an aqueous environment. So regarding the valence of the compound is determined by taking the absolute value of the charge on either the cation or the anion. So if we decided to use the calcium cation, then it will be the absolute of +2, which actually is 2. So the valence of the compound is 2. So the next thing we need to do is determine the total milliequivalents present in the solution. And the way we do that is to take the concentration, which is 2 milliequivalents in 1 milliliter, and multiply that by the volume of the solution that needs to be prepared. So that will be multiplied by 250 milliliters. The milliliters cancel out, and that ends up being 500 milliequivalents. So now we can plug all the values into the equation, which means we have 500 being equal to quantity of substance in milligrams divided by the 147 times the valence, which is going to be 2. We solve for the quantity in milligrams, so milligrams equals 500 times 147 divided by 2, and that is equal to 36,750 milligrams. But the question asks for the quantity in grams, so we do a quick conversion. And so 1,000 milligrams is present in 1 gram. The milligrams cancel out, and the answer is 36.75 grams. Let's take a look at this question, which says, how many grams of potassium sulfate, molecular weight 174.26, should be used to make 120 milliliters of a potassium sulfate solution containing 10 milliequivalents potassium ion per teaspoonful? Round answer to the nearest 100. Do not include units. So let's start by putting down the equation. You have milliequivalents is equal to the weight of substance in milligrams divided by the molecular weight times the valence. From the question, we know what the molecular weight is. It's actually 174.26. And so what we need to do next is find the valence. And so we have potassium sulfate, which is K2SO4. So when you put potassium sulfate in an aqueous environment, it's going to dissociate to give 2 potassium cations and a sulfate anion. And so the valence of the compound is obtained either by the absolute value of the charge on the cation or the absolute value of the charge on the anion. So if we use the sulfate anion, then it will be the absolute charge of -2, which is going to be 2. So the valence of potassium sulfate is 2. The next thing we want to do is determine the total milliequivalents of potassium in the 120 milliliter potassium sulfate solution. So total milliequivalents is going to be obtained by using the concentration 10 milliequivalents in 1 teaspoonful. We go ahead and convert the teaspoonful to milliliters. So 1 teaspoonful is equivalent to 5 milliliters. And then we multiply that by the volume of the preparation, which is 120 milliliters. So the milliliters cancel out, the teaspoonful cancels out, and you have 240 milliequivalents. So we can now go ahead and substitute all the values into the equation. We have 240 being equal to the weight of substance in milligrams divided by the molecular weight, which is 174.26. And then we multiply that by the valence, which is 2. We go ahead and solve for the unknown. So we have milligrams being equal to 240 times the 174.26 divided by 2. And that is equal to 20,911.2 milligrams. But notice that the question is asking for the quantity of potassium sulfate in grams. So we do a quick conversion. You have 1,000 milligrams. It's equivalent to 1 gram. So the milligrams cancel out. And the answer is 20.91 grams. This question says how many milliequivalents of potassium ion are contained in 10 fluid ounces of 10% potassium chloride solution. Molecular weight of potassium chloride is 74.55. Round answer to the nearest whole number. Do not include units. So here the first thing we want to do is put down the equation. So milliequivalents is equal to the weight of substance in milligrams divided by the molecular weight times the valence. The question already gives us the molecular weight of potassium chloride. So what we need to do next is find the valence of potassium chloride. So we have KCl, which is potassium chloride. When you put that in an aqueous environment, it dissociates into a potassium cation and a chloride anion. So the valence of potassium chloride is going to be equal to the absolute of either the charge on the cation or the charge on the anion. So if we chose potassium cation, the charge on that is +1, and so the absolute of +1 is 1, and so the valence of potassium chloride is going to be 1. So the next thing that we need to do is to determine the amount of potassium chloride in milligrams that is present in the 10 fluid ounce potassium chloride solution. And so the way we do that is to make use of the 10% concentration that has been given, which implies that you have 10 grams of potassium chloride in 100 milliliter of solution. We can convert the grams to milligrams. So 1 gram is equivalent to 1,000 milligrams. So the grams cancel out. So we now need to take care of the volume. So we multiply by the volume of the preparation, which is 10 fluid ounce. And then we convert the fluid ounce to milliliters. So 1 fluid ounce is approximately equal to 30 milliliters. So the fluid ounce cancels out, the milliliters cancels out, and you end up having 30,000 milligrams. So now we can substitute all these values into the equation. We have milliequivalents being equal to the 30,000 milligrams divided by the molecular weight, which is 74.55, times the valence, which is 1, and that is equal to 402. So I hope you found this video tutorial useful. If you did, be sure to like it and share it, and if you have any questions, leave them in the comments and I'll get to them as soon as I see them. If you like to learn more pharmaceutical calculations, tips, tricks, and strategies, then don't forget to subscribe and click the notification bell so you don't miss anything. Thank you so much for watching, and I'll see you in the next video.